How you doing? I'm Mr. Rose, and today, as you can see, we are going to tie in a whole bunch of our electricity concepts. A couple things to note before we get started. This is basically a review, again, or tie-in of all these concepts I have written here. Now, in the past, I have typically not referred to anything with the constant K, but I have continually used 1 over 4 pi epsilon naught. We should know that 1 over 4 pi epsilon naught, where epsilon naught is our electrostatic constant, is equal to K, which is just 9 times 10 to the ninth. Now, for simplicity's sake, I continually am going to use K for the purpose of this lecture, but again, remember, they are equivalent. K is equal to 1 over 4 pi epsilon naught. Second, this lecture is probably going to run longer than our 10-minute or 12-minute span in the past, because as you can see, I haven't prepped anything in advance. I wanted to draw this out rather as we went. Lastly, I am actually following some notes today. This way, anything that I have written down that I thought was important, I don't want to leave out for you. So with those things, keeping in mind those things, let's start. Here I have, forget about all of our equations to start, but I've placed a charge Q smack in the middle of this large box. Well, I know that Q is going to be a charge, and based on that charge, there's going to be some field that exists, some electric field that exists. So I'm going to draw just some electric fields at random points in space. I know, I don't really want that. I want this guy down there. I know that my electric field at different regions in space has a different magnitude. Electric fields get further away. They're smaller. Electric fields closer to a charge get larger. And I know that I'm going to use the formula E equals KQ over R, where Q is the charge or the size, the magnitude of that charge, and R is the distance in space that I'm looking at. So if I want to know the electric field at that distance, R is my distance in between that charge Q and where I'm looking for that electric field. I know my electric field is always pointing out radially from my charge, and I know my electric field is always going to be in the unit of a Newton per Coulomb. And I'm using a Newton per Coulomb here because we know that the electric field, Newton per Coulomb, is the amount of force needed in newtons to move that a charge of 1 Coulomb. Now, an electric field is a vector, which means if I have an electric field pointing in some random direction, in order to find that electric field, I'm going to want to break it up into components, namely an x component and a y component. So now I have an electric field in the x or the I hat direction. I have an electric field in the y direction, and I know my net electric field, or the magnitude of that field, is just the square root of a squared plus b squared using my Pythagorean theorem. Well, I know what you're thinking. You're thinking, what if there's another charge that exists? So if I have some other charge, that charge also produces some electric field. Well, if I now have 2 different electric fields, I want to know the net electric field at that point from this other charge. What I need to do is break that into components as well. So I have an x component and a y component. And now I'm going to add my x component to my x component. I'm going to add my y component to my y component. And then I either have an electric field in a vector notation, in I hat and j hat notation, or if I want the magnitude of that electric field, I'm simply going to use Pythagorean theorem of the square root of a squared plus b squared equals c squared, or the square root of x squared plus the square root of y squared equals r squared, so I know what that magnitude is, my total electric field. Now with that electric field, or with that charge I should say, comes not only an electric field, but an electric potential at random points. So I can have an electric potential there, or I can have an electric potential V over here, or an electric potential V at any one of those places in space. Now my electric potential is not a vector, and not a vector, it is going to make things very, very easy. To find my electric potential at any point in space, I'm going to come over and use my formula, V equals KQ over R. So now, this R is representing how far away in that region of space I am from my charge. Now an electric potential, again, I said is not a vector and is measured in a different unit, not a Newton per Coulomb, but electric potential is measured in a joule divided by a Coulomb. And the reason we use joule per coulomb is because it tells us how much energy is required to move 1 coulomb of charge in that region of space. So an electric potential is a little bit simpler than an electric field for simple reasons of it is a scalar quantity, and I don't actually need to worry about breaking things down into components. In other words, here, I needed my net electric field. I needed to have an x component and a y component. To find my net electric potential, I simply add total my potential at one spot plus the potential at two spots plus the potential at my third spot, etc., etc. Keeping in mind that I'm going to plug in exactly the number that I have. My electric potential V is just a number, a positive number or a negative number, which means my electric potential at any region in space could be positive or it could be negative. What do those positive and negatives actually mean? The positive simply means that my electric potential was due to a positive charge. A negative means my electric potential was due to a negative charge. So it's a little bit different than my electric field. If I move on from electric potential, well, I know if I have electric potential, if I want to move some charge, let's say another charge exists, I'll put it over here. Now I have another small charge over there, Q. I have one charge, I have another charge. If I have two charges, just like I have two masses, those charges want to interact with each other, just like our masses want to interact with each other. And if I have these two charges, I can find the force between those two charges as KQQ over R squared. Now here, my R squared is again, now instead of just a region in space, R is the physical distance between two specific point charges. Excuse me. R is the region in space in between my two specific point charges. Now, this is kind of a powerful and important thing to remember. We never ever want to forget what we've learned from mechanics. In other words, even though I have this large Q here and this small Q here, we all remember Newton's third law. Newton's third law tells me that the force on big Q due to little q is the exact same thing as the force of little q on big Q. That is going to be very important for us to know. Now, for some reason, students fall in love with this equation, KQQ over R squared. And you can see right under it, there is a much simpler and easier way to find an electric force because of a charge. So if I happen to know my electric field, I can do something much easier. I can say the force on some charge is due to the field. I just multiply my charge times my field, and then I get an electric force at that region in space. That is a much simpler equation. In fact, not only is it a simpler equation, it ends up to be a little bit of a more powerful equation. The reason why I say it's a more powerful equation is I can't actually use F equals KQQ over R squared unless I happen to know where all of my point charges exist and the region of those, the region of space of where those point charges exist. F equals Q times Z, notice I don't have to know anything about its placement. All I need to know is the electric field and the charge, and I can find the force. Now, because force is a vector, just like electric field, if I want to know what the electric force is here, I need to break that up into components. I need to have an x component and a y component, and once again, use either Pythagorean's theorem to find the magnitude of my electric force, or if I want to keep it in vector notation, I would have it in I hat, j hat, and k hat notation. We also want to note that if my force is positive, that means it is pointing in the direction of my electric field. So this would be an F positive. If my force is negative, it is pointing in the opposite direction of that electric field. So we've talked about force, we've talked about an electric field, we've talked about an electric potential. What we haven't talked about is anything with energy. We know we love energy. Energy is one of our governing laws of physics. So I know if I'm applying a force to a mass, that mass may move. If I'm applying a force to a mass and the mass is moving, that means there's work to be done. And we know work is also just a change in potential energy. So if there exists two charges and the force on those two charges, then that charge has a potential possibility to move. And I can find the potential energy in between those two charges. Let's say here, I can find some potential energy again. If I put a charge over there, of just QQ divided by R, where now again my R is the physical distance between those 2 point charges. Q1 and Q2 also happen to be the size or the magnitude of the electric charge. Now, just like we had an easier way to find an electric force as Q times Z, we do have an easier way to find our potential energy. Our potential energy, very simply, is the charge times my electric potential. Again, this is a much simpler equation, and if I happen to know the electric potential, or I can find the electric potential, why might I want to do this? I might want to do this one instead because, well, I know energy is a scalar quantity. I also happen to know that my electric potential, V, is a scalar quantity. So here I'm just plugging in straight numbers. If I know the electric potential is positive, I'm going to plug in a positive V and then the charge. If I know my electric potential is negative, I'm going to plug in a negative for my electric potential, and just solve directly. It's a much easier way to do things. Now, lastly, I know that my electric field is also related to my electric potential. And my electric field is related to my electric potential by the simple equation negative delta V divided by delta X. So what is that telling us? If I have a region in space, say there, and I can measure how far away that region in space is, a delta X. And since electric potential is such a powerful thing, and again, an electric potential is not it's not a vector quantity, but a scalar quantity. If I know the difference, a delta V, in my electric potential, I simply divide the two. In other words, I say my change in electric potential, V, divided by the distance, is that electric field. Dividing the two gives me the electric field in that region of space. If I know the electric field in that region of space, I know my electric field. That becomes a very important thing. What's the purpose of this negative? That's what you're thinking. Mr. Rose, why is that negative? I'll tell you why it's negative. The negative sign of this electric potential is almost a reminder that our electric potential, not our electric potential, that our electric field is always going to point in the direction of a lower electric potential. That's something that's very important to remember. Okay, so here you can see set up, I have a positive charge of 3Q here, I have a negative charge of 5Q here, separated by some distance D. I now have a point X in some region in space, and I want to know what is my electric field, E total, at that region in space X. To do that, I'm going to need to do a couple of things. Just like we did before, first thing I need to do is draw out my electric field. I know the electric field from my positive is going in this direction, my electric field here. I know based on my negative, I'm going to have an electric field in this radial direction, an electric field in that direction. And then to find my net electric field, again, electric field is a vector. I know I need to break this up into components. I know I need to break that up into components, but that component is just my X component. So all I'm going to do here is I need to find my electric field EX. I need to find my electric field EY. And I need to use then Pythagorean's theorem, a squared plus b squared equals c squared, to get my total. You might need a little bit, so if I know, for example, throw this guy right across, that distance d, I know my electric field is equal to k times 3q divided by my distance of r squared. Now I know my I just said r squared, I'm sorry. Kq over r, as we saw earlier over here. Now I know my distance r here is just using simple Pythagorean theorem. R is equal to the square root of d squared plus a squared. So I know my electric field, not in component form, my vector is equal to k times 3q divided by the square root of d squared plus a squared. Now once I have that number, I can use a little bit of trig. I know this angle, say theta. I know the inverse tan of theta is equal to d over a. So that can get me that angle, which is also a similar triangle, the same thing as that angle. Once I have that in my vector notation, I can add my x component to my x component, or in this case, that would be subtracting. I know I only have my y component, and then I find, again, my net electric field by just simply my Pythagorean theorem, where I would say my electric field total is equal, very simply put, my x component, so it would just be x squared plus y squared of my electric field due to the 3q, which I can call E1, and my electric field of my negative 5q, which I could call E2. Very simple, we've done that a whole lot of times. Once I know that electric field, why would I go through such a painstaking process? Again, look at all these formulas I have to choose from. If I know the electric field here, it's very simple for me to say, find an electric force due to some charge Q. I don't need to know anything else. It's just a simple straight multiplication. Now, what if I wanted to say, I found the electric field, let's find the electric potential at some other region in space, like the top corner, can't see that, like the top corner of my box or my cube over here. Well, electric potential is easier to find. I don't need to worry about any vector components for my electric potential. My electric potential, V total, is simply V1 plus V2. In other words, my electric potential from that charge and my electric potential of that charge. Well, my electric potential, let's come on over to my full review. Electric potential is equal to KQ divided by R, the distance in between. So I'm simply going to plug in V total. That is going to be, I'm sorry, I want my red color. My electric potential from my 3 is going to be K3Q divided by R, and I know that my distance is just A because I made that a square, A plus my distance here. Again, we just figured out what that radial distance is. So this radial distance we know, again, is just going to be the square root of D squared over A squared. And it's going to be, again, just straight plugging in K times negative 5Q over the square root of D squared plus A squared. And electric potential is so easy, I just need to throw those numbers in. And again, I keep my negatives exactly where they were negative. I keep my positives exactly where I put positive. And it's a direct sum or direct addition of the two. And lastly, we have a bunch of setups for field lines. Well, we know electric field lines are always going to point away from my positive. They're going to point radially away from a positive charge. And we know they're going to point radially inwards towards a negative charge. We know that if I have some region in space that has a positive and a negative charge near each other, we know that's called an electric dipole. And just like we have coming radially out from positive, coming into a negative, we have my same thing, my electric field lines going from my positive to my negative, or radially inward to the negative, radially inward to the negative, radially away from the positive. And you might notice that these field lines I'm drawing can never actually cross each other. Then if I have two charges that are the same charge, whether they're positive or negative, here I just happen to draw two positives, we know that my field lines again are going to come radially outward from my positive, radially outward from my positive, and it should appear some region in space in between the two that there may be some region in space we have a void of electric field lines, which is possible. The only difference between this being a negative or this being a positive, those two charges were negative, all of my arrowheads would be facing each other. So electric field lines are always pointing away or radially, depending on the way a positive test charge would go. Remember, electric field lines are pointing in the direction of a lower electric potential. Well, here are all my electric field lines. There we go. I mentioned that word electric potential again. So where are my equipotential lines? My equipotential lines are regions in space where the electric potential is equal all around that line. My electric potential or equipotential lines are always perpendicular to my electric field lines. So anywhere on these dotted blue lines, my equipotential or my electric potential is the same. In other words, it would be free to move an electron or a proton along those lines. Anywhere that those lines exist, just like electric field, we know the electric field lines, we know they can't cross. We know what electric field is strongest where the lines are the densest, the electric potential is largest rather, where the lines are the densest. Whew. Equipotential lines are imaginary lines that help us predict things like the electric field. And again, we connect all of them with the equations we still have on the board. Lastly, we have some parallel plate capacitor, which we've spoken about a lot, even though we haven't spoken about capacitors as of yet. So right now, all you need to know is that these are two plates that are charged oppositely. They have the opposite electric potential on both. These actually, the plates themselves, and I have them hooked up to some wires that are connected to some circuit that we're not worried about. The electric field in between is a constant electric field going from the positive plate to the negative plate, pointing in the direction of a lower electric potential, or we could say pointing in the direction of the direction that a positive test charge would move. Now, my plates themselves act like equipotential lines because it is the same potential all on that plate and the same potential all on the green or negative plate in this case, which means my electric potential lines are going straight across, vertically perpendicular to my electric field, and my electric potential decreases as I go radially across my my parallel plate capacitor. That's all we have to tie in all of these things. Sorry I couldn't get to Gauss's law and how we can tie Gauss's law in, but remember, Gauss's law is an observational law. It was found experimentally, and with Gauss's law, we often use to prove Coulomb's law, K-Q over R squared. Now remember, Gauss's law is equal to, I'm going to leave that one for you. I'll give you a hint though. It starts is equal to some E dot dr or dl. There's that second half of the equation. Don't ever forget that second half of the equation, epsilon naught over Q enclosed. And that Q enclosed is our imaginary Gauss's law or Gaussian surface. If you stopped it, you didn't think I told you, but good thing I did. Like I said, this video was going to last a little bit longer. We're somewhere around the 25-minute mark. There will be some editing. You'll probably see it. Fun game. Where did Mr. Rose edit? Where did Mr. Rose not edit? Anyhow, please feel free to like, comment, click, subscribe, anything you want on our YouTube channel. Thanks for watching, and I'll talk to you all next time.